Okay, so we're going to start talking about thermodynamics today. Just a lot of words, a lot of vocab stuff. So, for starters, what's thermodynamics? Thermodynamics is the transfer of heat. Transfer of heat and energy. So, we're looking at converting heat to energy, energy to heat, and all sorts of fun transfers like that. Okay, sounds awesome. So first thing we gotta talk about is temperature. Now, I'm sure you've heard this word before, but it is sometimes difficult for people to describe. So how temperature is defined is it is the average kinetic energy of the material, of the of the particles, let's say. All right, so if we're talking about a gas, remember a gas is made up of a bunch of different atoms that are all individually floating around. So these atoms are moving at a particular speed, and the higher the temperature that they have, the higher speed they have, and because it's related to the kinetic energy. So a cold gas, use blue, would have not as much movement as the hot gas. All right, so what you might have seen before is there's a wonderful graph that represents this. Okay, on the bottom we have your kinetic energy, and on the top is the percent. So it's just a frequency graph. So what's going to happen is if you're at a particular temperature, it's going to go up, it's going to curve, and it's going to go down, and it's going to do an asymptote here. All right, so what this means is that this is the materials, each one of them has a unique amount of kinetic energy, sort of, but most of the material is going to be right about here. All right, this is your mode. Since it's a normal distribution curve, it's also your median and your mean. So this guy right here is going to be your temperature. All right. Now this is for some material. If we cooled it down, what's going to happen is the average is going to go to the left. Now the curve is going to change a little bit. Curve is going to do something like this. And it's still going to have an asymptote. Right? So this material here has a lower temperature because it's got a lower average, but there's still some molecules that are moving fast and some molecules that are moving slower. It's just their average is higher. All right, so when we're talking about temperature, there are three common units. One of them is your friend Fahrenheit, one of them is your friend Celsius, and the third is your new friend Kelvin. All right, so let's talk about Celsius. Celsius, there's two numbers that are important. You have 0 and 100. At 0, you have water freezing. And at 100, you have water boiling at atmospheric pressure. Okay. Now, Fahrenheit, you have the same type of situation, but you have 32 degrees for water freezing and 212 degrees for water boiling. For Kelvin, you have 273 degrees for water freezing and 373 degrees for water boiling. Now we're going to talk about how to convert these, most importantly to Kelvin. In physics, we're going to use Kelvin pretty much all the time, but you should be aware of how to convert it to Celsius and Fahrenheit. So let's say you have a temperature in Fahrenheit. We'll jump over here. If you want to convert it to Celsius, all you got to do is you got to subtract 32 from it, and then you're going to multiply that difference by 5/9. This equals Celsius. All right, we're not going to practice this a lot. This is for your edification. You should know how to convert something. More importantly, now we're going to talk about how to convert Celsius into Kelvin. This is a lot easier. Celsius is just going to be plus 273.15. And that is going to equal Kelvin. All right. Now, the reason why I wrote the 0.15 is so you know that it is there. This is not a rounded, this is exact value here. So it is exactly 0.15, 0. Usually we just stick with the 273 though. One other thing about Kelvin is that when you're talking about it, there's no degrees Kelvin, all right? So if this temperature was 0 degrees Celsius, you'd put the degree sign and the Celsius there. However, for Kelvin, you're going to write 273 Kelvin, no degrees. So it's easier that way. Only other thing I can think of to help you out is if you want to write the degree sign on your computer for anything, really. If you want that symbol, you hold down the Alt key and then you type in the numbers 0176 and then it will put it in there. It works for Word, it works for internet, anything like that. So that's what temperature is. Temperature is a big one. Now we're going to talk about thermal energy. So what thermal energy is this is the energy within a substance. All right, so by energy, they're referring to the random motion. All right, so all that kinetic energy we talked about last time, that's thermal energy. We don't call it kinetic energy, we call it thermal energy because it's random. It's not in any particular way. If you added all those vectors together, it basically cancel out. So that's what makes it random motion. So it's the kinetic energy. If it were in one particular way, you wouldn't call it thermal energy, you'd call it work because it's got a particular direction to it. Alrighty, so that's what thermal energy is. Thermal energy is within everything with a temperature, which is everything. Cool. Now let's talk about heat. Heat is the transfer of thermal energy. All right, so the transfer of thermal energy, it always occurs one direction. By naturally, we mean spontaneously. It'll always happen one way automatically, but you can force it the other way. You just have to pay energy for it. Naturally, from hot to cold. By hot to cold, we mean from a high temperature, we'll call it TH, that's going to transfer to a low temperature, TC. So it doesn't mean that so which one has more thermal energy necessarily, but it does mean at which one is the higher temperature, okay? So for example, if we have a very large block of ice right here, so here's some ice, and we drop a very hot penny on this. So here's our penny. So this is going to be hot. And our ice is going to be, well, cold. Now, these could have the same amount of thermal energy. How could the ice keep up? Well, the ice is very big, but the penny is very hot. So they could add up to the same amount of thermal energy. You're not going to have to figure that out quantitatively. You just should be aware that hotter things have more thermal energy, and bigger things have more thermal energy. There's not going to be a comparison between the two that you'll have to do. But once they touch each other, there's going to be heat transfer. The heat transfer is going to go from here to there. All right? This will keep going until they reach the same temperature, until they reach equilibrium. All right, and that's what heat is. So we're going to talk about conduction. So conduction is heat transfer through contact. So there has to be touching for this kind of thing. There's going to be interaction between the atoms. What is going to occur is you're going to have a hot something here. Well, this is just some hot material. I'm going to take a block of metal, like a thin beam, and I'm going to touch the end of that metal to there. Now this first atom that's right here, here's some of the atoms that are showing up. These atoms are vibrating because atoms are in motion because there's some kinetic energy there. And what's going to happen is this atom is going to run into that hot piece of metal, we'll say, the hot plate, the stove. And it's going to run into there. It's going to take some of that thermal energy away. Now this atom is going to be warmer, and it's going to run into this atom, and this atom will get hotter. So that motion will carry down. Now eventually, this atom is going to be colder for a long time, but it will get warmer as the heat makes its way from left to right in our picture. So they're bumping into each other, and they're passing the energy one by one. It could be the atoms, it could also just be the electrons, but it's the same process either way. Now, there is a formula for this, all right? More on a macro scale, but we'll still talk about it. So the formula for this is Q over delta T, that's a little t, is equal to K A delta T, big T, divided by L. All right, you don't have to memorize this. This is on your formula sheet. It's in the thermodynamics side. I can't show you right now. But let's talk about what all these wonderful letters are. So let's talk about the left side first so we know what we're going to be equaling here. Q is going to be your thermal energy, so your heat. All right, typically heat, so how much heat is going into something, how much thermal energy is traveling. All right, since it's energy, your unit is going to be joules. For your delta T, this is a little t, this is going to be time. Time is going to be in seconds. So this is how much heat travels per second. So altogether, this is going to be in watts. Sometimes you'll see watts showing up. Okay, now on the left side, so this guy is going to equal how fast heat transfers. So A stands for area. It's the cross-section area, right? Cross-section. So, for example, in this, it'd be the cross-section of this beam here. It could be a square, it could be a circle. It's whatever it is. All right? This is going to be in meters squared. Now, it's in the numerator, and it makes sense because the bigger the cross-section, the more heat can flow through faster, right? The more heat per second. Okay? The next letter, let's talk about this delta T here, is this is the change in temperature. Change in temperature. Okay? Now, so this is the temperature difference between point A and point B. So for this guy here, it could be the difference between this hot temperature and this cold temperature. That would be the delta T. The bigger the change in temperature, the more heat will flow because there's more of a difference. There's more of a difference in the temperature. There's more of a change in kinetic energy. If they're very similar temperatures, heat's not going to flow very quickly. All right? So the units for this are going to be in Kelvin, or they're going to be in Celsius. Now, it doesn't matter. The reason why it doesn't matter is because 1 degree Kelvin is the same size as a 1 degree Celsius. Remember a little while ago when we converted, you just added a number. So they have the same slope, they have the same width per degree. If it gets 1 degree hotter Kelvin, it's going to get 1 degree hotter Celsius. They have the same size in that respect, so it doesn't matter as long as it's a delta T, and it's very often going to be a delta T. As long as it's a delta T, you can use either one of these two. If there's no delta, you have to use Kelvin. L is the thickness of the material. All right, this is going to be in meters. It's in the denominator because the thicker it is, the harder it is for the heat to travel through that amount of stuff. So thinner stuff will have heat go through faster, thicker stuff will have heat go through slower. That's why your winter coats are thicker than your summer coat. All right, and the last one, you probably can predict what this guy is this is going to be a constant. All right, so the name of this constant is going to be the thermal conductivity constant. Thermal conductivity. All right. So this is going to depend on the material. So we'll tell you a couple of them just so you can get an idea here. Now it's going to have some units. It has some horrible units. So you have to get watts out of there. So it's going to have watts, and it's going to divide by meters in the denominator because you have meters squared divided by meters. You have to cancel that out. And it's going to have Kelvin in the denominator. Sometimes you'll see a Celsius in the denominator. It's the same thing. All right, so let's give you some ideas about what it's going to equal. So for wood, right, if you want the K for wood, it's going to equal 0.16, thereabouts. And there's lots of different types of wood. These are hardwoods, woods that you would use in buildings or whatever. So if you want for concrete, so, you know, stone, concrete, that kind of stuff, that's going to be at 1.7. This means that wood is a better insulator than concrete because a smaller number here means less heat per second is going through it. All right, give you an idea about glass. Glass is about 1.05. Now, again, there's lots of different types of glass, but generally it's about 1.05. And so it's a little bit of a better insulator than wood, than concrete, but not as good as wood. And finally, steel. What would you expect for steel? Would you expect a big number or a small number? What do you think? Steel is going to have a large number. Steel is going to have a very large number. It is 17. It's a whole number. So it conducts 17 times as much heat as glass does. It's a metal. Should make sense. It's a good heat conductor. All right. So we're going to do a practice with this one now. A single paned window in your house is that wide, that tall, and has a thickness of 2 centimeters. This glass has a thermal conductivity of 0.84. Assume that the outside temperature of the glass is 5 degrees Celsius, inside temperature is 20 degrees Celsius. How much energy are you going to lose out of the window in an hour? Okay, so we're thinking of our window here. So there it is. So let's write down our formula. Q over change in time is going to equal your K times your A times your change in temperature divided by L was the letter. Okay. Well, we know some stuff about our window here. It's 0.65 wide. 1.25 tall and 0.02 thick because that's in centimeters there. All right, do you think you can plug everything in? We'll give you a head start to do that. Go. Okay, all right, we're back. So Now plugging in things here, we're looking for what Q is equal to. We're going to divide by delta T, so in an hour. So we're going to have 60 times 60, right? Because this is per second. 60 seconds in a minute, 60 minutes in an hour is equal to K. The constant for glass is 0.84 times your area, so it's a rectangle, so 1.25 times 0.65. Remember, if you can't remember that formula, it's on your formula sheet. Your change in temperature, so 5 degrees outside, 20 degrees inside. So we're going to put 15, 20 minus 5, and then divide by the thickness of 0.02. So we're going to do some math here. We're going to times 15, divide by 0.02, times 0.84, times 60, times 60. So we're going to get around 1.8 times 10 to the 6 joules. All right. It's not unusual for them to use mega or kilojoules for stuff like this. 1.8 megajoules. Is that a lot? It depends on what you're comparing it against. All right, so there's one skill we need to have. Hey, we're going to talk about convection now. Convection is another way of heat transfer. Convection is heat transfer through movement of a fluid. All right, so what's a fluid? A fluid is going to be, oh, you can't see that color. A fluid is going to be a gas or a liquid, all right? Either one, doesn't matter. So a fluid is something that can move around, so not a solid. A plasma would also be a fluid, but we're not going to worry about that. So let's talk about convection. So here's a candle. The candle is on fire. So there's the fire. It's gorgeous. All right. What's going to happen is the candle is creating heat. The air is going to get hot around here. But the fluid is going to move. The fluid is going to rise. The hot air is going to rise up. If you put your hand here, you would feel the heat from the candle. You're feeling it even though you're not touching the fire. You're feeling the hot air that's rising up from there. So this type of heat transfer is called convection. All right, so the hot air rises. This cold air that is surrounding, that's not next to the candle, is going to flow in to the space created, and it's going to go around. As this air rises up, it's going to touch your hand. Your hand isn't as hot, so it's going to cool down, and then it will sink back, and it will make this cycle right here. This is called a convection current. This is a very common thing. This is how wind is created in the world, because air is hotter, it rises up. Air is colder, it sinks down. With the earth spinning, it creates horizontal motion. This is also how your air conditioner works. Your air conditioner pulls in air from the ceiling because that's where the hot air is. It pumps air out. The cold air goes to the ground. This is how the tectonic plates move. The mantle within the earth is a liquid. So the plates float around on there. That's how ocean currents happen as well. All of this stuff. It's how your oven works. Maybe you have a convection oven. That's how convection works. Now we're going to talk about the final type of heat transfer, which is radiation. Radiation is the type of heat. It's heat transfer. Heat transfer through waves. All right, what kind of waves? Through electromagnetic waves. All right, so what are you talking about? Let's say you have something hot. Let's say you have something that is whatever temperature. Here's a box. Now what's happened is all things emit electromagnetic waves. You are emitting electromagnetic waves right now. But what happens is the energy of the waves is going to be proportional to the temperature of the waves, generally speaking. So you are standing here, you are emitting waves out, but they're not in the visual spectrum. Because remember, the energy of the wave is proportional to the frequency. So you have low frequency waves. So you are right now emitting infrared waves. That's what you're emitting. That's why if you put your hand close to something, you can feel the heat coming off of it. That's the radiation. It's infrared because you can't see it. This is how night vision goggles work. Night vision goggles work at night because they're picking up on those infrared waves. If you get something hotter, so let's say it's hot, what will happen is the frequency will increase, the wavelength will decrease, and it will start to emit things that are not only infrared. It will start to emit also visible light. It'll start in the red colors. If you have a stove that you forget to put the pot on there when you turn it on, it will turn red. It will turn red because it is emitting the bottom color of the visible spectrum. If you keep leaving it on, let's say you put it in a furnace or something like that, it will start to emit yellow light as well. Remember, because each part of it is a slightly different temperature because of the curve. And if you really heat it up, some of it will heat green and some of it will emit blue. Does this mean it will look rainbowy? No, it won't look rainbowy because it's emitting all the colors eventually, which means that it will look white. It'll emit white light. And this is what is happening for your friend, the sun. All right, so here's the sun. The sun emits light by radiation. Now, so the sun is emitting white light. It's emitting white light because it is so hot, it is emitting all the colors together. So that's why it looks white. All right, so something special about radiation is, the reason why we're mentioning the sun, is it can travel through a vacuum. Through a vacuum. So this is the only one that can travel through a vacuum. You do not get heat from the sun through conduction. You would not want heat from the sun through conduction. Nor do you get it through convection. There isn't any airflow that happens here. You get it through radiation. You've also experienced this if you've ever been at a bonfire before. Here's you. You're standing at a bonfire. The bonfire is very large. The front side of you gets very hot because it's receiving the waves. The back side of you gets very cold because it's not facing those waves. All right, we know it's not convection because if it were, then the back side of you would be warm as well because it would be heating the air itself. All right, there are formulas for radiation. You don't have to know them at this level, only if you're going into a college level thermodynamics class. It's not important here. But those are the three types of heat transfer. The only one you have to numerically describe is conduction. And the other vocabulary, the heat and the thermal energy, we're going to talk about those a lot. So you'll have to get familiar with those terms. All right, like and subscribe for more videos.